Okay, yeah. So, in fact, what initially I was planning to do when I suggested to Shajesh was something different, but then I rethought about it and I felt that I can come to that part later, maybe in some other talk. So I was thinking that when Shajesh spoke about the sequential Stern-Gallagher experiment, one can use that. Uh, one can use a sequential Stern-Gallagher experiment and also demonstrate the need to have a complex wave function or a complex state vector. But even before one does that, actually, one can even examine a few elementary things and come to appreciate the need for the complex wave functions. So today, I think I just plan to stick to that part, and maybe, in some future talk, I can cover that as well as some other related issues. Okay. So you see, if we put together this whole notions, which I would like to call quantum quirkiness. How do you spell quirkiness? Quirkines?
Yeah, that's what I would think.
If then there are this whole complex of notions which would fall under the quantum quirkiness, and they could be, for instance, wave particle duality. Okay, which essentially says that if you have a particle, say a free particle of momentum p, then p is a particle attribute of the momentum of the particle, and the particle also happens to have the wave attribute, and that wave attribute is the wavelength. Then there is a relation between these two, that the momentum of the particle is inversely proportional to the wavelength. And if the particle happens to have the energy E, okay, then it is related to the frequency of the associated wave, and that relation is h nu. So if you multiply both this numerator and denominator by 2 pi, and they are also often stated as P is h cross k, where k is the wave number and E is h cross omega, where h cross is nothing but the Planck's constant h divided by 2 pi. So in some sense, actually, these two relations, they encompass almost all of the quantum quirkiness. Okay. The other way to look at the quantum quirkiness is that that the observables are, related to what is known as operators, and very often the.
So Rishi, just a quick clarification. The energy that you write here is the total energy of the.
Yeah, the energy of the particle, and the P is the momentum of the particle. Okay.
Yeah, and is there like if is there like there is a classical notion of kinetic energy here? Like, can I write the energy as P square over 2m? That kind of thing.
You can always write the energy as P square over 2m in the non-relativistic limit. The whole idea of this relation here, for example, E equals h cross omega. So if E is the energy of the particle and omega is the angular frequency of the associated wave, okay, then if you compare and contrast it with a classical wave, okay, then you see that the energy of the wave, classical wave, is never related to the frequency. It is related to the amplitude. Okay.
Yeah.
So
Yeah, that's true.
So in that sense, and the momentum of a classical wave is not related to the wave number or the wavelength. So in that sense, these relations are actually, they summarize in 3 letters the entire quantum mechanics. It's actually, it hits at the core of quantum mechanics. It's 3 letters. Okay. And the fact that observables are related to the operators, and hence this leads to that there are a pair of canonically conjugate observables. Okay, for which, for example, for concreteness, if I take xpx, they don't commute. And a direct consequence of this is the uncertainty relation okay. So it says that for a certain pair of canonically conjugate variables, the system never has simultaneously the precise value for these 2 observables. It's not that you are not able to measure, it's just that you cannot prepare a state which simultaneously has precise values. And if the delta x and delta px are the uncertainties in these 2 variables, and of course so on and so forth for the other components, then the product of uncertainties is always greater than or equal to h cross by 2. What this means, what this implies, that if you have a particle of pure momentum p, okay, then it implies that its position uncertainty is infinite. Okay. There is another quirkiness, and that you have the equation of motion contains I explicitly. Okay, this is not true of any of the classical, and in fact, one way of seeing that the complexity of the wave function actually also can seem to follow from the fact that you have this iota appearing explicitly in the equation of motion, whether you look at the Heisenberg equation of motion or the Schrodinger equation of motion, and that you have wave function, or alternately the state vector, is an object which is living in a complex vector space, or it's a complex object. Okay, and now what I hope to convey is that actually all of these things are related. Okay. And they are all in some sense, actually postulational or axiomatic. There is no way to, so these are all related. The complexity of psi and the fact that you have differential operators and non-commuting observables, and that you have an equation of motion which contains I, these are all related. Now let's try to look at it from some very elementary standpoints, that we are trying to describe a free particle.
Yeah, I'm digressing again a little bit, Rishi,
yes.
just
yeah.
for like, suppose somebody has done like classical wave theory, he would say that, oh no, I have seen iota there because a possible solution is e to the ix or ik dot x.
Okay, okay. So the good point. So now the point is, the way we use complex numbers or complex functions in classical theory, it's only a mathematical tool. We do not use them to represent any physically measurable, observable. Okay, it's just that, you know, thanks to Euler's formula, the exponential, you know, functions have some nice mathematical properties. So it's a very handy tool. Okay, but at the end of the day, in our analysis, we always take the real part. We you know, turn the wave equation or any differential equation into an equation for a complex variable, because, you know, if you have oscillatory functions and you do it in terms of sines and cosines, okay, then of course, you know, upon differentiation and integration, sines and cosine, you know, interchange, and the analysis algebraically becomes quite involved, because then you have to work through the trigonometric identities. The beauty of the Euler's formula and the exponential function is that, you know, when differentiated, it returns to itself. Okay, so it simplifies algebra a great deal, and it kept tracks of because it contains the sines and cosines as its components. So it beautifully kept tracks of the relations between the sines and cosines and all trigonometric identities. And at the end of the day, you know, you take the real part of your solution, and so your solutions are never e to power ikx in your classical physics, because it's representing a physically measurable observable. Amplitude of a wave is a measurable observable, and that's why it's always the real part, real or imaginary part, which is again a pure number. Okay, so I hope that clarifies.
Comment there.
Yeah.
Sometimes classical quantities, especially the refractive index, the real part and imaginary part are related. Both are independently real, as you're saying, but they seem to be connected to each other, right? The dielectric constant, once you know the real part, you completely know the imaginary part also. There is a relation between them. As you're saying, both are independently real, but this complex connection seems to be there in that classical electrodynamics also. But I agree that physical quantities are real.
It's not. It's not. I think it's. It's. We are using this, you know, the complex nature only to understand as a mathematical tool. It's not that, you know, any physical quantity is actually complex. Okay, so
yeah,
it's, I think, only a workaround. Complex functions in classical physics is only a workaround to make sense of things, because complex functions are very powerful. You know, once you have anything which is an analytic function, then one can employ the power of complex functions to deal with a lot of things and extract a lot of details about the physical system. But there is no physical quantity in classical physics which is actually complex. That's what I'm trying to say.
But wouldn't that be true in quantum mechanics also?
In quantum mechanics, you do not have an option. Your wave function is complex. And that's why, you know, I mean, so it's related. That's why you cannot measure the wave function.
Yeah.
Okay, so it's related. But
I guess that is what
mechanics, just in quantum mechanics, as I hope to demonstrate, that you do not have a choice of real wave function. Okay.
Sure.
Yeah, that's the difference. Okay. So
one more
let's
comment.
try and see. Yeah,
one
sure.
more comment in A. Is there a connection between omega and K? The dispersion relation is not.
Yeah. So omega is a function of K.
Okay. But not necessarily a linear.
Yeah. Depends upon the situation so omega is a function of K. Yeah. Now, so let's take, for example, a free particle of momentum p, and since it's supposed to be described by a wavelength lambda. Okay. Now, since it's a free particle, it has a precise momentum, right? So let's try and describe it by let us say, for the time being, let's look at just the forget about the time. Let's look at the psi as a just a function of x, a cos kx. So k is to pi by lambda x. So let us assume a real wave function. Okay, and see, so now this describes apparently a wave of constant momentum and a wavelength lambda. Okay, oscillatory. Now if we draw this wave, so of course it has infinite extent. Okay. Now your yeah. So there is one more thing, that you have this wave function is supposed to be describing the probability of finding a particle. Okay, so your mod psi squared dx is supposed to be the probability of finding a particle between x to x plus dx. Okay, now so if you plot the mod psi squared, then this is how this looks, right? Pardon my poor drawing. Okay, now but the point is, if you have a free particle, then your uncertainty principle tells that the particle with a sharp momentum, we have absolutely no information about its position. Okay, we have zero information about its position.
Why did this increase in size? The wave.
This is my poor manual drawing skills. This is just
square,
a cosine,
right? The square of the
just a square
amplitude.
of cos square. That's it.
But square, if it is less than 1, is psi less than 1, or is there any such rule? Just curious. Yeah.
No, I have not given any units here.
Okay.
Okay, I've not given any units here. Okay, so this is of course supposed to be a normalized this thing, but the point is that if you have a purely real wave function, okay, and this is what mod psi squared looks like when you plot it, then you see that there are regions where the chances of finding the particle are large, and there are regions, there are points where locations where it is small and it is zero at some points, right? So this goes counter to this expectation that we have a zero information about the location of the particle. Okay, so the what is it that should be compliant with the fact that given a wave with a well-defined momentum and wavelength, the information on position should be zero. So we are looking for a function whose mod squared is constant and yet it is oscillatory. Okay, so the only function which fits that bill is a to power ikx, because then it implies that your mod psi squared is constant. So your probability of finding a particle anywhere in the world is actually a constant, and yeah, so it gels well with the expectation from the uncertainty principle. A real wave function won't fit the bill. Okay, a real wave function will actually not fit the bill. Okay, so you have a plane wave. So Prachi, you know, unlike your classical waves, where at the end of the day you will be required to take a real or imaginary part here. Here your psi itself is given by this. Okay. This of course does not mean that.
But why couldn't I choose, let's say, a sine of kx here? What would have been wrong if I had just chosen a sine or a cosine of kx? Because if I do the square, that will also show me that kind of probability function, right? Up there.
No. So what do you want here is, okay, what do you want here is that if you plot mod psi squared as a function of x, there should be no information about where the particle is. Okay. So your sine or cosine or any other real function, it will have a profile in x. Mod psi squared will have a profile in x, which is different from constant. What we need is a function which is constant. Okay. Whose mod square is constant.
Oh, I guess you are saying that the total probability is constant, right? But total probability, does it have to do with the total probability? Because
the
ideally
total probability is 1. Total probability of finding particle somewhere is 1.
Yeah.
Okay. So what does the uncertainty principle tell you? That if you have a particle with a definite momenta, okay, so delta p is 0,
yeah,
then delta x is infinite. So basically there is no information about the location of the particle. The uncertainty is infinite. Okay.
Yeah.
Yeah.
So
your mod squared should be constant. Because if mod square is has a profile in space, then that would mean that you have some information about there is more probability of finding a particle here than over there, which goes against the expectation of the uncertainty principle.
Yeah, I guess what will help a little bit is if you relate the wave function with the position or the momentum. Because a person who is coming from the classical wave, like classical wave theory, will know that solution of the position is given in terms of a sine cosine phi. And then they can find out the energy and they can find out the velocity.
So it is given by psi. So now if you look at how this function evolves in time, so you can, for example, okay, so at psi as x equal to 0, at t equal to 0, you can have a e to power ikx. Okay, but psi as a function of time would be given by, so this will be a cos kx omega minus omega t plus I a sine kx minus omega t. This is in terms of, so you have an oscillatory function whose mod squared is constant. Okay, and this is forced upon you. Okay. Now, as Merzbacher would have you believe, there is another way of looking at this. What Merzbacher says is that, if you have an infinite general wave, okay, associated with with say particle of momentum p and wave number k is given by, suppose if it is going in a positive x direction, okay. So this is given as cos kx minus omega t plus delta sine kx minus omega t. Okay. But delta is as such, as of now, an unknown. So if you can show that this delta is complex, okay, then you have it that your psi is complex. Okay. Now, you see, we have written this both superposition of cos kx minus omega t and sin kx minus omega t because of the so-called linear superposition in quantum mechanics. Okay. Linear superposition in quantum mechanics. Now, if you say that this wave is, it's independent of, say, arbitrary displacements in x and t. This wave is independent of, arbitrary displacements in x and t. Okay. Why? Because, we know that if it's a wave with a pure momentum p, then there is no information about its location in x. Okay. So then it should also, the phase constant in each of these should not have any physical meaning. Okay. Then your cos kx minus omega t, sorry, plus say epsilon plus delta sine kx minus omega t plus, what I am doing is, suppose, if you displace it in space or time by some amount, that would be tantamount to having some constant phase factor epsilon, phase constant added to it. But this should be completely independent of this, because there is no information about the location of particle at x. So then this should be equal to some normalization which is the function of epsilon times cos kx minus omega t plus delta sine kx minus omega t. Okay. The statement that any arbitrary displacement in x and t shouldn't have any physical consequences.
And why is that requirement so?
Because
it's not the psi that changes, right? Psi square should be not having any physical consequences.
No. So the point is, here you have, if you linearly superpose these two things, and should not have any physical consequence, because the if you change the phase constant by a constant amount,
I guess it is easier to think in terms of exponential, right? If you make a phase change in exponential.
Prachi, the point is, just a minute, I'll come back to your point. Just a minute. Now, if you have this requirement, now my point is that, you know, this requirement cannot be imposed for example, classical waves. Okay. Why? Because, you know, for classical waves, any displacement in phase or any changes of phase, you know, there is a physical amplitude at different phase points, right? Which is different and which can be measured. Okay. And that's the reason perhaps that, you know, you have to impose this on the psi itself and not the mod psi star. Okay. The whole idea is that, you know, what should be the condition imposed on psi? Okay. For example, if this psi were to describe a classical wave, okay, then what I'm saying will not hold true. I'm saying that any arbitrary displacement in space and time should not have any physical consequence, which means this, if you add epsilon to both sine and cosine, then other than changing the overall normalization constant, as you can see, it should be similar. Okay. Now, for a classical wave, you know that the different phase points have different amplitudes, and that amplitude you can go and measure, right? Here you are not able to measure psi, and that's why it should not really. Okay. This actually, if you impose this requirement and, you know, just use this cosine and sine angle addition rules, it trivially gives you that your delta has plus minus I, and hence your A is nothing but e to power I epsilon, which is just adding a phase vector, okay, to the wave psi. So if you choose delta equals plus I, okay, then as now you can see, Prachi, that, you know, this gives you your complex. The whole idea is to try and understand as to why do you need complex. So your delta is forced upon you to be complex, and the fact that your delta is purely imaginary is forced upon you indirectly by the Heisenberg's uncertainty principle, because you should have no information of the particle in the x, and that's why this wave, if you make any spatiotemporal changes, you know, arbitrary displacements in x and t, then it's just tantamount to adding some phase constants, and it should not have any physical consequences. This cannot be true of classical waves. Okay.
But again, Rishi, if I got the logic right, you said you would like psi to be not physical, or psi to be physical. Sorry, you said psi should be physical, so this should have this condition, and so this condition holds. But we know that psi is not physical.
No, when did I say that psi is physical?
When you say that there should be no observable consequences. Isn't that a requirement of a physical psi?
I guess the thing he was relating to is that the probability, like that psi square should be constant.
Yeah, that's the key, I suppose. Yeah, I agree. Psi square.
I spoke about the constancy of the mod psi squared and not psi, and that requires the psi to be complex.
Yeah, that I got. Like that was the earlier conclusion made. Yeah, and.
No, here, you know, if any, the point is, if you make arbitrary displacements here, you know, if the phase constants have a physical meaning, then you will not land into a mod psi squared, which is constant.
Got it.
Okay.
Mhm.
So that's why this equality must hold. And the reason that you cannot have this requirement for classical waves is because for classical waves, you know for sure that the amplitude is a measurable quantity. And that's why, you know, at different phase points, you can measure the amplitude. Okay. And that's why there is a difference of amplitude at different phase points.
Mhm.
Okay. So this tells you that your delta is could be plus minus I. Both are, you know, perfectly, it's just a convention. If you choose delta equals I, then, you know, psi xt becomes your. Now, this does not mean that you cannot have a real wave function. You can have a real wave function at a given point in time. If you add, for example, two exponentials, you know, e to power I kx, e to power minus I kx, and they sum up to cosine kx. But that is only at a given point in time. The time evolution will ultimately, you know, give you a phase factor in that as well. Okay. So you can have at a given point in time a real wave function, but ultimately, you know, when you factor in the time evolution, it will turn out to be complex. Okay. So this is another way of, and as you can see, that all this makes use of the, you know, all these things are read, the complexity of the psi, the immeasurability of psi itself, and the fact that, you know, your energy and momentum are represented by differential operators, and hence there is a commutation relation for x and px. Okay. And once that is there, then the uncertainty is inevitable consequence of that, and that has it that a particle with a pure momentum is infinite in spread, and there is a zero information about the position. So all this complex of motions are, you know, they are related. Now,
so maybe I should go back and ask, like, why
yes.
You probably said it, like, and I didn't register it. Like, why psi square, which is probability, right? Why psi square has to be constant? Like, total, I can understand the total psi square has to be equal to 1. But if you are doing it between like an interval, let's say x plus delta x or t plus delta t, why do I want it to be a constant value?
Because it's a free particle, that's a reasonable thing to expect, right? A free particle should not have any.
If it's a function of space, then it would mean that the, you know, not all points in space are same. You know, there is more, it is a probability density, right? This mod psi squared is a probability density. So if your mod psi squared has a profile in space, non-trivial profile in space, it would mean that the probability of finding particles at different axes is different.
Exactly. And that is what is the positive side of oscillatory function that you showed on the previous page was showing.
No, it shouldn't. No, that is, I think he was drawing psi there, not psi square.
Cos kx.
Yeah, for cos kx.
So
he wants it to be constant. Yeah, the second graph is what he wants.
Exactly. So that's why this is wrong.
Yeah, that's wrong. Yeah.
This will not work. That's why this will not work.
Correct.
And you know, that's why.
Yeah, but let me ask again. So the point is, when I say about probability density, let's say, is it not okay to say that it should be different at different location?
In general, yes, but not for a free particle.
Not for a free particle. Okay.
For a free
just
particle,
a comment here. Unless you include quantum vacuum fluctuations. Because we say that they can create and destroy its own, right? Or is it? I mean, what if, maybe that's just a very broad.
Yeah, but Sajesh, okay, I'll have to think hard before I can answer. But you see, the quantum vacuum fluctuations, I think unless you do something non-trivial to dig out that energy, okay, in which case you no longer stay in a free particle domain, right? How do you dig out the energy from the vacuum? You cannot do that using a free particle, okay?
Great. Yeah.
Yeah.
No, I agree that it should be constant, no doubt. Yes, because it's a free particle. There is no parameter. It has to be constant. I completely agree. Wherever you go, however you go. That's a very reasonable requirement. I think so.
Yeah. No, it's required. I mean, without that, you will not be you've not been in compliance with the uncertainty principle. Okay. Now, there is another way of looking at it, which of course is slightly, I mean, I think I'll have to do more work on that, but I just want to point out and that is, say, so you have a particle of momentum, free particle, of course, of momentum P, and of course it is related to the wave vector K, and its energy E is related to its angular frequency omega. Okay. Now, suppose you go to a different frame with velocity v. Okay. Okay. Then, of course, we know I mean, since we are in the non-relativistic regime, we can make use of the Galilean transformation. Okay. So if you are boosting to a frame with velocity v, say for simplicity only along x direction, so then your x prime is x minus vt. Okay. The question is, what is the momentum p prime in the boosted frame? So of course, it is related to momentum p in the old frame by this, right? Now, the problem is, so lambda, so this particle with momentum p is associated with a wavelength lambda. Okay. So what would be the wavelength lambda prime in the boosted frame? So it will be p minus mv, right? So what does this tell you? That the wavelength of the particle lambda is not same as the wavelength lambda prime as it appears in the boosted frame. Okay.
What is phi?
Sorry?
What is phi there in the denominator?
Oh, no, it's not phi. Sorry. It's not phi. It's p. Sorry.
Okay.
I did not. I overwrote it. That's why it appeared like phi.
Okay.
So the lambda prime is h upon p prime, and p prime is p minus mv. Okay. So lambda is not equal to lambda prime. Sorry. Right. Now, let us look at the classical wave. Say classical elastic wave. Okay. Now we know that the phase of this wave is nothing but the number of peaks per unit wavelength and all that, right? I mean, so the phase of a classical wave is actually invariant under Galilean transformation. Okay. So the phase phi of a classical elastic wave, for example, okay, is say suppose if you have a wave, elastic wave, moving with speed capital V in the medium, in the rest frame of the medium, quote unquote rest frame of the medium. Okay. Then this is the phase. So this phase being given by just a number of peaks per unit wavelength is actually only supposed to be Galilean invariant. Okay. So phi prime is suppose here this V and V prime are the speed of the wave. Okay. This is small v and this is big V. These are the speeds of the wave. Okay. Now, since the phase is Galilean invariant,
why is the phase Galilean invariant?
it's just the number of waves per unit wavelength or per unit time, I mean, number of peaks, and so that shouldn't change.
Why?
Why that number can, if you just go to a different frame, why should that number of peaks?
Because phase is not a number, right? It is a ratio. It's a ratio of the length of the wavelength divided by a part of a wavelength. It's a dimensionless quantity, but not necessarily a number, right? It's not a property of how many of you are coming in. It's a fraction of the wavelength.
But if so you have, K is number of waves per unit length. So K times X is the number of waves in the length X, right? Now, if you count this number of peaks that cross you, why should that depend upon your velocity?
That I agree. The number of peaks.
That is what it is. That is what it is.
It's a fraction. Number of peaks will be. Is that
what it is? Yes, that is what it is.
Okay.
You have one peak in 2 pi, right?
Yeah. One.
Just because I'm moving, that number will not change.
That I agree. But how many? Like I thought, phase was a fraction of the length between the.
No. It's the number of peaks per unit length, or if at a given point, the number of peaks that cross.
Isn't then you're assuming that x minus vt is a integer number of lambda? Is that an intrinsic assumption here?
No, that need not be. That need not be. That did not be integer. That did not be integer. That doesn't have to be. The point is that it doesn't have to change.
Okay.
From one frame to other frame.
Like what why can't I think about it like when we talk in terms of transformation from one frame to another frame, like we talk in terms of like, oh, what kind of quantity is being transformed, right? So you say, oh, scalar transforms a certain way, they don't change. Vector transform certain way, they change.
So this number is a scalar under Galilean transform.
So this is, why can't you think in terms of that, Shajesh? That phi is not a vector quantity or a tensor quantity.
So Shajesh is trying to understand that, what makes phi a scalar under Galilean transformation.
Oh, yeah. Okay. Yeah.
Yeah.
Because I don't see that, the number of waves per unit length, would just change because you're moving with a different speed. Okay. So now when you just make use of this transformation for x prime and b prime, okay, what you get is, okay, so what you get is phi prime is same as 5. That is what you are imposing. So your lambda prime turns out to be same as lambda. And of course, your omega prime has a standard, I think, the Doppler formula, for this omega prime. Okay. So sorry, it is actually sorry, it is small v by capital V.
So, like, I mean, when you solve it, you actually don't impose this condition that lambda prime has to be equal to whatever you wrote in the previous statement. That lambda prime was equal to.
Just a minute. No. Why is this not erasing? Okay. What I'm saying is, omega prime is omega into okay. So this is your standard Doppler effect. And here you get lambda prime same as lambda. Whereas there, your lambda prime is not same as lambda. Okay. So what could have possibly gone wrong? So actually it turns out that this for the classical wave, the wave amplitude is a measurable quantity, right?
Oh, remind me, wave equation, is it Galilean invariant? Probably not, right?
No. So your wave equation is not invariant under Galilean transformation. It is invariant under Lorentz transformation.
Yeah. So
for the electromagnetic, yeah.
So a wave, yeah, whatever that implies.
No,
yeah.
this is, I'm talking about the phase.
Yeah. No, I get it. Yeah.
Okay.
So these conclusions really hold in classical wave or just a wave theory, if it is Galilean. If you do not want to accept.
The point is that the discrepancy between these two is that actually we are comparing apples and oranges. Okay. So what is happening is that in the classical elastic wave, the classical wave, elastic wave, the phase and the wave amplitude is Galilean invariant, because if it was not Galilean invariant, okay, then you could figure out preferred frames by measuring, because amplitude can be measured, right?
Mm-hmm.
So you can then figure out the preferred frames. Okay.
Now again, help me here. Okay.
Yeah.
So you're saying x minus vt is the same as x prime minus vt prime, correct? That's the phi was equal to phi prime. So lambda is equal to lambda prime because you're saying x minus vt is the same as x prime minus vt prime. Is that the conclusion, correct?
Yeah.
And this should
put in, you will get this. If you just substitute for x prime and v prime. Okay.
And wouldn't this conclusion hold in Newtonian wave physics then? So wavelength should be the same?
For the classical waves, this holds true.
Wavelength remains the same.
Yeah, that's the classical waves. This is true.
What about Doppler effect?
This is Doppler effect.
So we just
Omega
write it
prime
as wavelength
frequency.
or speed of light over this, is it? I thought wavelength
Yeah.
also changes in a different frame, isn't it? No, or I might
No,
be
no.
I might be
No.
interpreting it wrong. Yeah.
No, the classical, this is true, and it's the Doppler effect is in terms of the frequency.
Okay. Yeah.
The velocity and the frequency changes, the wavelength doesn't change.
Okay.
Yeah. Okay.
Because I was wondering about the diagram where you compress the source into the observer, so there are less number of wavefronts coming towards
Less number.
Yeah.
So the frequency
That's
changes.
phase, is it? It's not the wavelength. Okay.
Yeah. So now the thing is that your classical wave, your classical amplitude is Galilean invariant. Okay. Because if it was not, then you would be able, because you can measure the amplitude, so you would be able to figure out the preferred frame. Okay, so it has to be Galilean invariant. Now, psi being complex, it has no obligation to be Galilean invariant.
Maybe the right way to say it is that it is Galilean invariant in a frame going horizontally, right? Why amplitude is in the opposite direction or perpendicular orthogonal direction? Is that the reason why it is? Otherwise, it is just a length, right? I would say, like an ocean wave, I'm thinking, has a height h of bounds. I would think if I were to move in the direction of the wave.
Okay. By amplitude, what I mean is that, it will change with the phase, right? So you're affecting the phase factor. Okay.
Yeah.
By boosting to a different frame. So amplitude is multiplied by a cosine or some such factor. So you are affecting the phase. So, it's not just the maximal amplitude I'm talking about. By amplitude, what I mean is that the classical wave itself. Okay.
I see.
It's not just because the phase factor will be affected, right, through the Galilean transformation.
Yeah.
Okay.
I see what I see.
Yeah. So then you can, but psi transforms non-trivially under the Galilean transformation. In fact, it picks up a gauge transformation. Okay. And that's why, since it is a non-trivial gauge transformation, so this condition that lambda prime not equals lambda works out for the psi. Okay. Now, of course, this can be demonstrated in great detail. Maybe in some Sphics talks, I'll actually take it up. I have to really work through a lot of, but this can be actually done beautifully, and one can actually demonstrate the connection. In fact, there is one connection that I'm trying to explore and understand, is that there is a deep connection between the gauge transformation and the Lorentz transformation. Okay. And I see that there is some connection there about these two here as well, because there is a way to understand this even from the Lorentz transformation perspective. Okay, so it turns out that I will not go into the detail of that argument because I have to still understand that argument in its full totality. But you can actually, instead of employing the Galilean transformation, you can actually use the Lorentz transformation, and it can be argued that you must use Lorentz transformation, and you can explain this non-equality of lambda prime, that even if your V is small, you still are supposed to be using Lorentz transformation, and you can actually understand this. So there are two ways of understanding this. Either you can understand it within the framework of Galilean transformation, okay, in which case you can connect it with the gauge transformation, the non-trivial transformation of the wave function, or you can also connect it with the Lorentz transformation. But that part I have to still fully understand, so I will not go into it. But definitely, maybe in some future Sphics talk, I will take it up when I actually, completely work it out. But there is another way too. So I mean, so for example, here the psi being complex. In fact, it must be complex. It must be complex because if it is not complex, then it can be measured, and if it can be measured, then then of course lambda prime has to be same as lambda, because if lambda prime is not same as lambda, and this Galilean invariance doesn't work out. Okay, so psi being complex, lambda prime is not equal to lambda. Okay, so we have no obligation to believe in this result for the classical wave. Okay, that lambda prime is same as lambda. Now, connecting to the question which Prachi asked, one reason that psi is complex is because there is an explicit iota factor in the Schrodinger equation. Okay. So for example, forget about that. Let us look at the wave equation. And for simplicity, let us look at the one-dimensional wave equation. Okay. Now let us assume, psi to be complex. Yeah, I have to look at the screen and write here. I mean, somehow I'm not used to this looking there and writing here. Of course, it's not that fine. Now, so when you just do the simple time and special derivatives of y and plug it into this equation, okay, then what you get is that both A and B separately satisfy your wave equation. Okay. Sorry. Okay. So as you can see, but there is no, A and B can both be freely chosen. And there is no relation between A and B. Okay. So that's why, you are free to complexify the whole problem. Okay. And at the end of the day, just take the real or imaginary part, and both of them satisfy the same wave equation. So physically, they do not, give you anything new or different. You have the freedom to choose between A and B, and it doesn't take away anything, that is.
So if I am free to choose, why wouldn't I set B equal to 0? Why make my life miserable by having a complex number there?
No, you are not making your life miserable. You are in fact simplifying your life, because when you solve the equations in terms of the complex exponentials, it simplifies your labor. Okay. At the end of the day, you see, even for your light, you take the real part of it, right?
Mm-hmm.
So my point is that the complexification in the classical theory is only a mathematical tool, but it's easier to deal with exponentials than with sines and cosines. That's it. Nothing more, nothing less. Okay, now let's try and do the same thing for the Schrodinger equation. Okay. If you look at your Schrodinger equation, and for simplicity, I'll just use it in one dimension. Of course, it's trivial to extend it to the 3 dimension. So IH bar dou psi by dou t is equal to H psi. So I am talking about a free particle. Okay. Okay, I'm talking about the one dimensional. Now suppose you write your psi of xt as okay, axt plus ibxt, and when you take the derivative and plug it in, what you find is that dou a by dou t is minus h cross by twice m dou x squared dou v by dou t. So you get basically two coupled differential equation. So your A and B are not independent, okay, and there is no way to untangle them. You need both to have a total psi. And this is also, you know, the probability density is A squared plus B squared. So you need both. Okay. Yeah. Now, you see, the only twist is you have this fellow I sitting here. If you don't have this I sitting here, then you will see that A and B will uncouple. A will just like the previous equation. In fact, we have such an equation, right? You have a diffusion equation. Schrodinger equation is nothing but the diffusion or a heat equation with an iota plugged in there to complexify your solution. The diffusion equation has a perfectly real solution, you know. So it's the presence of the imaginary quantity in your differential equation, be it Schrodinger equation or be it the Heisenberg equation of motion. Okay. And this imaginary quantity is required to make sense of this wave particle duality. You know, if you want to have both, then you want to describe a particle with a fixed momentum and the wave number k, then you better do it using a complex number. And by the way, I must also say that, you know, the way complex numbers enter in quantum mechanics is different from the way they enter in the classical physics. For example, in the classical physics, okay, suppose, you know, you want to find the real part of a complex number z. Okay. Then how do you find the real part of z? One by 2 z plus z star, right? Now, in QM, your state vector is a k psi. Okay. A complex k psi. It lives in a complex vector space, and there is no way to obtain, a real part of this state vector, because there is no way to add a Kate and a bra. They both belong to different spaces. So you cannot get a real part out of a complex part by adding a Kate and a bra.
But I can add to the complex part of psi itself, right? Like, why can't I do ket plus ket star?
No, there is no such thing as ket star. There is a ket and a bra.
I mean, suppose a wave function, we can take a complex conjugate, right? I'm allowed
No, so that's what Dirac says is that, you have a complex conjugate notion for the ordinary complex numbers, and the analog of this complex conjugation is complex imaginary, which is like the relation between Z and Z star. It translates into relation between Kate psi and a bra psi.
But that's a dagger, right?
Yeah, but that's the, you cannot just take a psi and a Kate psi star and add them.
Yeah, but I'll get a ket itself, right? I'll get a ket plus ket star will be a ket itself. No, should be okay. No, am I not allowed to do that?
There is no star operation. You ever do the adjoint operation?
No, but think of it like, why work with the Dirac representation? I could have just lived with like psi x of t as Schwinger. No, Schrodinger did it.
No.
In his.
So I mean, the point is,
then it's not a member of the space, actually. Yeah, then it's not. Yeah, when you take the complex conjugate and if you get the real part, then it's not really a member of the space itself. I see. But that should be, it doesn't. Okay. For example, a free particle state, just for argument, e raised to ikx is a wave, is a ket, correct?
Yeah.
I'm in the position basis, and I take a complex conjugate, then that's also a allowed state, right? And if I add them,
no, you can sure do it at the level of wave function.
Yeah,
you can sure do it at the level of wave function. Nothing wrong. But the point is, Rajesh, suppose you do it like nobody stops you from having at the give. That's what I said in the beginning. Nobody stops you from having at a given time psi at x equals t equals 0 is, for example, it's perfectly legitimate. Okay, this is what cos kx.
Yeah.
This is perfectly legitimate. Okay, the whole point is that this is only possible at a given instant. The moment you look at the time evolution, you will have a phase factor and it will be actually complex. It cannot stay real forever. Okay.
Yeah. Okay.
And the whole formalism of, the way the principle of linear superposition, works in the classical and quantum physics is different. Of course, you have a linear theory in classical physics, right, where principle of superposition works, where you have, suppose, you take a vibrating string and superpose it with a similar vibrating string, and you get a state with twice the amplitude and 4 times the energy, right? But quantum mechanically, you take psi and add psi to itself, you still get psi. There is no such thing as a double the amplitude and 4 times the energy. So you multiply psi by any constant complex number, and it's still the same state. Psi and C psi is the same state, but C is any complex number. So the way linear superposition works in quantum mechanics is different from how exactly it operates in the, because of this aspect of quantum mechanics. That psi and c psi are the same. And it is, so all this actually are related. I mean, these are, I mean, they are all pointing towards the same, I mean, be it wave particle duality or the fact that you have observables represented by differential. So for example, okay, forget about quantum mechanics. This is true in ordinary classical mathematics, where D is a differential operator. Right. The commutator of...
I'm going to ask you the same question here. Like, I mean, when we give the equation that you gave in the previous case, like the origin of that equation is different. But here also, like in classical physics, we work with this Hamiltonian, right? Canonical operators. And you create the whole formulation of describing the motion with these commutation relations between something, right? X and P and something like that.
In classical physics.
Yeah, in classical physics, like there are different types of formulations, right? So
no,
like the Schrodinger equation is a consequence of having H operator acting on psi, giving you the energy. Like that's the idea there. And same kind of equation should exist in classical physics also, but it exists differently.
No.
Like there is a Hamiltonian formulation in classical mechanics also, right? It's just that because this commutativity is there between X and P, that's why like there is different like different equation form that you...
Objection. You said just because there is commutativity, it is not just. That commutativity is everything here.
I know, but that's not an objection. I completely agree to that. Like there is an inherent something which is different about quantum mechanics. I totally understand that. But what I'm saying is that I guess like a parallel should be drawn is like why the Schrodinger equation is the way it is in quantum mechanics in comparison to what is the classical analog of this equation in the Hamiltonian formalism.
Okay. So, I think I'll just, I mean, my perspective is that I think it's a wrong question to ask because the Schrodinger equation, all this, I mean, I said in the very beginning that we are not really trying to explain anything from something more fundamental. Okay. If I have given a feeling that, I have explained the complexity of psi from something very fundamental thing. That's why if you can see that, I wrote everything. I said these are all related. These are different aspects of the same. Okay. So all that we have tried to do here right now is that, what is this connection, and ultimately these aspects are forced upon us by experimental observations. Okay. So the way I would pose the question that you have posed is not that why Schrodinger equation takes the form it takes. The real question is why classical mechanics takes the form it takes. Okay. So the answer to that question is classical mechanics takes the form it takes because quantum mechanics takes the form it takes. So you imagine, if you have...
Well, Rishi, that is not very helpful. Okay. Like, I mean, if you go in circles, that is not very helpful. One, I will say no question is a wrong question. Every question needs to be answered. Second thing here is that, I mean, we come with a classical background and we encountered something which was not able to be described by classical mechanics. Then you come up with something. So if you think in terms of a chronological fashion, you have to say, oh, why was it different from what it was previously known? And I mean, I guess like this is the way you should try to answer it. I mean, I completely agree in the hindsight, you will say, oh, this is the real thing. And that is the limitation.
Okay. So let me, I think let me explain my statement. When I said that, it is a wrong question, what I meant is that, at this point in time, what is it that we understand as axioms of quantum mechanics? Definitely, tomorrow, if we have a better and a deeper understanding, okay, then we would like to explain this axiom in terms of even more basic things, but we will have a starting point, right? So all I'm trying to say, I'm not saying that, that there cannot be an answer to the question as to why Schrodinger equation takes the form it takes. I'm saying that as of now, this questions about wave particle dualism, about the form of Schrodinger equation, about the differential representation of observables and their non-commutativity, these are all, at some level, these are all equivalent statements. And as of now, we do not have an understanding which explains these things from even more. So our current understanding is that, this is the way to explain the experimental results. Okay, this is our current understanding. I'm not saying that, it will never be possible to understand. And of course, we should try and maybe at some point understand as to why the mathematics of quantum mechanics takes the form it takes. Okay, certainly. But at this point, okay, so I can add one thing. For example, you can ask that, you have this xd, which is a commutator of x and differential operator, which is 1, which is non-commuting. X and d are non-commuting. In fact, just forget about that. I often ask my students that, okay, I think I have taught only quantum mechanics once. I should not say I often ask. When I taught maybe 7 years ago, delta x, delta kx, right? There is such a relation for classical waves, right? This is greater than 1 something. Suggest, do you remember such a relation for a wave group? So if you take a collection of plane waves whose wave vector says in a band of delta kx, okay, then their x spread and the spread in the wave space, there is a relation like this, right?
Yeah. This is almost the same as what you wrote earlier if you replace P with H bar K, right?
Exactly. So what I'm saying, so what I tell my student is that, okay, if I multiply both the sides by H cross, okay, then boom, we have quantum mechanics. So we already have a relation or a similar relation which is in classical mechanics, and you just multiply both sides of equation by H cross and you have quantum mechanics. So then why are we making so much fuss about quantum mechanics? We have such a relation for classical waves, right? If I take a bunch of plane waves of different k's, and if the spread in the k space is delta k, okay, suppose I take one-dimensional waves and the spread in the k space is delta k, then I end up with a wave group whose spatial spread is delta x, and the product of the delta x and delta k is greater than 1. And if I multiply it by H cross, then I have my Heisenberg's uncertainty principle. So why are we making so much fuss about quantum mechanics, and why we didn't fuss over it in the classical mechanics when we have a similar thing already? And we already have xd in classical mechanics, right? It's non-commuting.
Or the statement would be anything that has Fourier transformation inbuilt will have this property, right?
Exactly. This is just the Fourier, the Fourier theorem, nothing else. Just multiply by H cross and then you have it, because this follows from ordinary Fourier analysis.
So
to me, because this bothered me a lot. In fact, this bothered me from the time, I was in TIFR, and one eminent physicist at TIFR, in one of the discussions in the tea time, said that why are people making so much fuss about quantum mechanics? He said that, you have such a relation in classical waves, and it's there. And, he said that he wouldn't really make a fuss over it. Just multiply by h cross, and then you have Heisenberg's continuity principle. And he just stopped there. He said that he doesn't make a big deal of quantum mechanics. He said he made a statement that quantum mechanics is there in classical mechanics. Okay. And of course, I did not agree with the statement. But of course, it also bothered me. But I thought hard a few days over this. And what I realized is that the problem is not, of course, you have delta x, delta k greater than 1. That is there. The non-trivial aspect of quantum mechanics is when you identify h cross k with p. Okay. So the contribution of Heisenberg or all those people is, when you are identifying, h cross k with p, then you are making a bold statement. You are relating the wave attribute to the momentum of a particle. And that is quantum mechanics. P equals h cross k it has all the quantum mechanics rolled into these 3 letters. Quantum mechanics is just P equals h cross k and E is h cross omega. In fact, even E equals h cross omega also follows once you, factor in relativity, because, E and P are the components of the 4 vector. So omega and k also transform as a 4 vector. So it's implied, So all of quantum mechanics is that.
No, right? Relativity doesn't have h bar in it, right? E and P can transform like that without h bar, and you're good.
Yeah. No, I never
said
that.
H bar is not there in relativity, right?
No.
Yeah.
I did not say that h bar is there. Yeah. What I said is that once you have a relation between P and K, it implies a relation for the other component in relativity.
Yeah.
I'm saying that, and by the way, in fact, relativity requires that quantum mechanics is not correct. Okay, that quantum field theory is the right way of going about it, and that can be seen in the very commutation relations. So you have x and px. IH bar, right? Now, once you require special relativity, okay, then x is a part of 4 vector, right? And your P is also a part of 4 vector, right? Now, relativity requires a democratic treatment between space and time, or all components of 4 vectors should transform in a definite way in the Lorentz transformation. So, if you want, your QM to comply with special relativity, then there should exist a commutator for T and E, the spatial, the temporal components of 4 vectors for position and momenta, right? If you want a democratic treatment of space and time, if quantum mechanics is to comply with relativity, then there should also be a commutator for T and E, but such a commutator doesn't exist. And why is that? Because T is only a parameter in quantum mechanics. It's not a dynamical variable. So there is no operator corresponding to T. There is an operator corresponding to E, but there is no operator corresponding to T. Now it turns out that suppose if you construct an operator corresponding to T, okay, if you turn T into an operator, then it can imply a unitary evolution operator, just as the energy is a generator of time translation, right? E to power minus IET. If there is an operator corresponding to T, then there will be a unitary operator, okay, where T epsilon, where T, so this operator will actually translate in the energy space, and it can be shown that, if such an operator exists, then the spectrum of Hamiltonian is unbounded from below. So if the spectrum is unbounded from below, then the stability will be compromised. And that's why, when you go from, if you want quantum mechanics to be in conformity with relativity, then this route, although this is the most obvious suggestion to comply with relativity, that, you have a similar operator relation between T and E. Okay, so promote T to operator so that E and T are both operators. But now you want to comply with relativity, so you cannot promote time and position to the operator. So the only other way to treat them both democratically is to demote them to parameters. Okay, so you demote both T and X to parameters. And hence, as a parameter, they can only appear, as a field as some function of the parameters X and T. So now your X and T are both parameters. And so that's why, you need a field, because that's the only way they can appear. So you need so any compliance of relativity with quantum mechanics requires you to have a field notion. And now you quantize these fields. This is another way of looking at why, the standard way is that, okay, once you have relativity, you can have pair creation, and, the particle number conservation is not a good way of going about it. So ordinary quantum mechanics, where the number of particles is fixed, cannot be, a right way. You should have a theory which is capable of describing arbitrarily large number of particles. Okay. And such a theory better be a field theory, because it has infinitely many degrees of freedom. That's one way of looking at it. This is another way of looking at it. That X and T have to be demoted as, just parameters of a field, coordinates of a field from the operator. They have an operator status in the this thing, but they lose that operator status. So your fields are operators in quantum field theory. And everything is constructed from fields.
Where did you say that they had operator status?
Sorry?
Where did you say that they had operator status? And
No,
then
I'm
they were
saying,
demoted to the parameter status in field theory? So what? So they had operator status in classical mechanics, quantum mechanics, or?
No. Okay. Your position, momentum, energy, they are all operators in quantum mechanics, right?
So, okay. So you're talking about quantum mechanics. So
yes,
they are.
Yes, but time is not an operator. In quantum mechanics, time is not an operator. Okay, but relativity requires you to treat space and time democratically, right? And even
Like
though
they
we
should
have
transform according to Lorentz transformation. Democratically, that's not necessary. Time is special, right? Everywhere, even in relativity.
But the point is, if your equations have to have a covariant then your quantum conditions are fundamental, right? So the zeroth component will have a corresponding relation there. If you write your equations in a covariant fashion, then you will write all having as gamma mu. The zeroth component will be time.
But that's a tensor equation there, right? X mu P mu is equal to IH bar delta.
Yes, so you will write the computation relation between X and P in terms of x mu and t mu.
That's not
Okay.
very obvious. Yeah. I mean, T is special. I agree. Even everywhere, right? T
No,
is.
T is special, but I'm saying that so because T is special, it comes in the way of, you know, your you cannot have an operator. I mean, for example, one can ask as to, you know, what if one constructs a time operator? What are the difficulties, right? And definitely, you know, in fact, even the standard quantum mechanics, in fact, that's why the Schwinger and Tomonaga, their treatment of even the standard commutation relations in field theory, forget about this. Even when you demote space and time to just mere coordinates of fields, I mean, the parameters of fields, even then the commutation relations for field and the momentum, it is equal time commutation relation, right? It's not a covariant treatment.
Mhm.
So
And that's
basically,
where I
you are
think
saying that in quantum mechanics, we cannot do a measurement of time.
in quantum mechanics, where time is not a dynamical variable. In fact, the interpretation of time energy uncertainty relation doesn't follow from a commutation relation. It has a very different origin and different interpretation. In fact, forget about that. You know, even the statement that all canonically conjugate variables have commutation relation, there is no commutation relation for phi and L phi. Or at least it doesn't, there is no commutation. I mean, you can write it, but it doesn't have the same interpretation between phi
I
and
think
L.
we are struggling because probably I think the whole idea is to understand dynamics, and we are talking about dynamics in time, right? Something is evolving in time. And I agree, one would like it to be covariant. That might be possible, but typically that's a difficulty, I guess, that it is the equations are written for the evolution of these apparatus, right? So that's inbuilt in there.
Yeah, but in relativity, we are able to write equations where we don't single out time, right? Or we write it in terms of this proper time, which is invariant.
But that Dirac equation does that, right? Doesn't Dirac equation do that?
Dirac equation, it does that, but the treatment of time is actually covariant. I mean, you can write it in terms of it's a Lorentz covariant, you know.
Yeah, Dirac equation is
covariant.
Lorentz covariant, but
exactly,
then
that's
you
what
cannot.
I'm saying.
Yeah, but you cannot write t comma e there, right?
Huh?
You would not write t comma e there either.
Yeah, you're not writing t comma either. True.
Yes.
So the
Saying one
treatment
can
of
have covariance in the
but
equations
treatment
without. We just have to avoid this commutator, I suppose.
but so that's why Dirac equation is not able to explain the, you know, that's why we need quantum field theory. It's not a complete picture.
So Heisenberg analog of this also exists, right? Delta T, delta E is greater than equal to H bar.
True. That's what I'm saying, that analog does not, there is no corresponding commutation relation between T and E. That's what I'm saying. And the interpretation of that is very different from XPX.
So what's wrong in saying that time commutes with Hamiltonian? Oh, it does not, right? So time.
No, not time
no.
commute with. I am saying the way
If
you
it is
wrote like X and D, one could also come up with some X and another D, which is delta del by del T kind. One could have. And it could still show some kind of like it will not be commuting with each other.
Yeah, no, I think it is okay to write this statement T comma E is IH bar. It's just that the Hamiltonian is time independent. Oh, that's a challenge, I suppose. Hamiltonian is time independent for the whole universe in a sense, and then it will not commute.
No, but Sajesh, when my very first objection is, how are you, when you write T comma E, are you treating time as an operator?
Yeah, I mean, it has to be, right?
Yeah, once you do that, then you will have this. That's what it has been done. That's what I'm trying to tell you. It has been done. This has been tried. Okay. And you have corresponding to the e to the power IET, you have a corresponding unitary evolution operator whose presence leads to a spectrum which is unbounded from below, which does not tally with the experimental observations. That's what I'm saying. It has been tried. You can see this. I think it's also discussed in Mark Shednicki's book on quantum field theory. This is also discussed in one Pauli's book on quantum mechanics. There is one book by Pauli on quantum mechanics. I don't remember the title. Okay, but this is also discussed in Mark Shednicki's book on quantum field theory.
Okay, so follow the same analogy which you did for the position and D operator. And like develop that line of thought and think like why. Okay, so there existed in the wave theory, there was a spread in delta X and delta K. But why couldn't I think of in terms of a spread in delta T, and what is the corresponding thing that relates to it?
Like, so yeah.
one quick connection that I can think of, like, I mean, we say that in Schrodinger equation, like the operator E has to be written as IH cross del by del T. And where is this connection actually coming from? So it's the same kind of idea that you wrote that, oh, there is an X comma D, which is equal to 1. It doesn't commute. Same way, T comma del by del T does not commute. And why can't we ask ourselves the question that as we do delta X spread, we can do delta T spread also. What is the quantity which is the Fourier transform of this particular thing?
That's what I'm saying. The challenge with that kind of computation relation is with the interpretation of time. I mean, as I told you, it has been tried, but there are bottlenecks when you go ahead. It has been tried, I'm saying.
I guess like that is what I'm asking. Like, I guess I am interested in knowing about the bottlenecks, because like a parallel kind of thing should exist. And that's where probably the origin of this recognized with del by del T type of structure does come in.
Okay, I would say that when you say that the parallel kind of thing should exist, it's a strong statement in the sense, just a minute.
When I say...
just a minute, there's a call, just a minute. Vishwanath. Hi, how are you? हाँ, मैं आपको थोड़ी देर में कॉल करता हूँ. Actually, I am giving a talk right now. Yeah, I am on an online talk right now. मैं अभी मैं करता हूँ, थोड़ी देर में करता हूँ कॉल, ठीक है? But everything is this. Naveen told that everything is fine, right? It got over. अच्छा, हाँ, अभी मैं थोड़ी देर में करता हूँ, ठीक है? I am almost done. I'll just call you, okay? हाँ, मैं अभी बस I am done. I'll be just calling you in a while, okay? Yeah, okay, yeah, thanks. Bye. Hello. Yeah. Okay. Now, what I'm trying to say is that I mean, see, we must understand one thing, that time is something we don't understand. So when we say that it must exist, that statement would mean that we so strongly understand the behavior of, I mean, X, Px, E is one thing and time is another thing. So when we say that it must exist, when people tried, it was of course purely from the expectation that in SR, special relativity, they expected a covariant treatment of space and time, so they moved on. But I think everybody acknowledges that we don't understand actually time. I mean, one of the pressing problems in quantization of the theories of gravity is actually how to incorporate time. So time is something we don't understand actually. I mean, as Sajay said, it's something very special, and we don't really understand actually what time is. That's what I wanted to say.
like I'm quite sure that there, like I mean, people must have explored all these ideas and like somehow came with the conclusion that this kind of thing cannot exist. But like considering that I do not know it, and I would like to follow the parallel of the same thing. Oh, I can write x comma del by del x, considering they are Fourier transforms of each other. Same way I can think in terms of this and what happened. Like, I mean, probably this is the right way of, in my mind, it is the right way about any student of physics will be that, oh, okay, like what happened? I mean,
Sure. No, I mean, that is a perfect, I mean, that is a perfectly, it's a genuine and a beautiful attitude. That is how, we all, that's how, I mean, I also was wondering about all this. That's why I explored, and I found somewhere that there is an article, this is there actually, I'll share with you. It is in a footnote of Pauli's book. Okay. It's discussed in a footnote of Pauli's book. And then later on, I found that when I was looking at Schrodinger book, on the motivations for quantum field theory, this is discussed in Schrodinger's book. But more than that, I haven't had a chance to explore. I mean, no, I'm saying
this should not be very surprising, right? I can write this probably. So let's say this is t, and let's say this is a function of a proper time s, comma, the Hamiltonian. And I say this is evolution, and this is 1 on 1 over I, let's say. And then I simply say this is d by ds of t, where t is now some operator. So maybe this is not that bad. But I'm sure there are challenges. I hear you. Oops, sorry.
Yeah.
I hear you, what you're saying. Yeah.
And I think even this fact that the spectrum is unbounded from below is not difficult to see actually. I mean, it's a very straightforward consequence. It's a very straightforward consequence. Yeah.
But I have a comment on all the way back, like when you say that I think the basic assumption that you made is that a wave function should, or anything that is observable cannot be complex, right? That was sort of your basic idea, right? Because we observe only real quantities. Now, I say that I measure 2 real quantities.
Yeah.
And there seems, suppose I see a connection between the 2 real quantities. Like, and the connection is not just a linear relation or anything, they are analytic. The combination x plus iy, with the I having this complex structure, having an analytic behavior in it, analytic in the complex plane sense. And I'm saying there are physical variables like that in classical mechanics, a refractive index and absorption, like dissipation, fluctuation. It seems to be there. So then why are we so much sticking on to that fact that if we can measure something that cannot be complex, when there are all these examples sitting in there? And I also say this because causality, in fact, implies that you have to go into this complex plane, like Kramer's chronic relation. I'm sure that in signal processing, you cannot avoid complex functions. There it is a necessity probably because they are causal relations. So I'm saying causality will require a causality plus a response will force us into complex functions. So why are we so afraid of it? Why do we say that classical mechanics does not deal with complex quantities?
Yes, 2 comments. Okay, 2 comments. One thing is, what I said is that, I mean, introducing complex function as a tool is one thing, but that does not exist, I think any quantity, even in classical physics, which is actually measured and which has complex values. Okay, that's one comment. And the second comment is, I think in quantum mechanics, now let me come to the, suppose you have a complex is nothing but 2 real quantities, right? Now, for measurement, if you have 2 real quantities to measure, it will require 2 measurements, right? cannot measure it in one measurement. This is where the trouble in quantum mechanics lies. Make one measurement to disturb the system. So making two measurements, you're not measuring the same system. This is what Dirac has said, that if you have a complex quantity, and then it will require you to measure two things and two separate measurements at that. And each measurement, is a process which will disturb the state. So you cannot claim to have, in classical mechanics, you can make measurements, and the very assumption is that you're not disturbing the system.
Well, Rishi, I would like to make a point here, like, because you brought out the need of wave function being a field was very nice in your previous slide. And one should consider the theory, like the Maxwell's theory, built upon the whole idea of fields. That's where, like, you build in like your electric field and magnetic field. They are not measurable quantities. You don't measure them. You measure something else. So whenever you are doing an observable, it will be a square of the field that will be appearing. But there is a similar analog that kind of exists somewhere there also. Like I understand there are subtle differences, but a line of thought is existing in the classical mechanics along the same ideas here. Like wherever you make the connection of Lorentzian invariant, like that kind of tells like, oh, that demands there should be a field kind of, like these x and t should be demoted to the parameter. I mean, those kind of ideas are existing in Maxwell's theory. So, like, I mean, I don't know.
No. So those kind of ideas are existing in Maxwell's theory, but again, those E and B are in principle, they are okay. So again, this you have a classical. Okay, the question could be that, okay, why is the electron field or neutrino field not classically measurable, but the photon field has a classical measurability, right? E's and B's are in principle classically measurable, right?
Well, not measurable. The fields are never measurable. You will always measure the interaction where, of course, you disturb the system. So you will always measure probably the force between them or intensity or something else. But all I'm saying is like going in the lower domain of it is an idea that is always there. So like I'm just building upon the comment Sharish is making, that there is this like complex nature that is existing.
Or maybe I can add to that, like if Dirac has said that two quantities form complex, so there are two measurements involved. But what if the two quantities are completely related and in such a way that they form an analytic function and they exist, like absorption and refractive index of a material, they are completely real and imaginary part of a function. It's a requirement. Causality imposes it. Causality, like causality is a very necessary thing. So it is there in there. So I'm saying, just saying that just because there are two quantities, it cannot be real. That seems to be a little too much, even if it is Dirac. I would like.
No, Sadesh. Yeah. I mean, of course, I mean, it doesn't matter. I mean, we have to question everybody, not just Dirac, because it's about our conviction, right? Not about what Dirac says. So my conviction is not because what Dirac has said, but the argument that Dirac gave, that because, when you make a measurement in quantum system, you are actually, so making two measurements is, you cannot come to the reality of a thing by making two different measurements, because each measurement disturbs the system and disturbs in an incalculable way. So it is
not if they are for example, if you measure energy twice, that's okay, right?
Oh no, that is fine. That is fine. Of course, but then, I mean, that way, once you single out a given quantity and then It's like, in the your
or commuting observers like LX, LX and L square. Right. So I'm saying, what if this L square and LX are the real and imaginary part of a complex function? Then we are good, right? Like that, at least that part of the argument that it requires two measurements does not work. Like, what if they're commuting observables?
Yeah, for commuting observables, of course, you can make as many measurements as you want.
So then, at least
I guess
there is a way out of it.
And that is not what it meant. When he said like two measurements, it is supposed to be the two measurement of the same quantity, real and imaginary part. So it can never be the commuting observables in that sense. But I am saying
of course.
Yeah.
Of course, you need the same, of course, because the real and imaginary part of the same function.
Yeah.
Not of two different functions.
But the deal here is that if I'm doing a measurement of, let's say, one observable, let me iterate it again. So I have made a measurement on, let's say, position or LX, for example. I have disturbed LY completely. I have disturbed LZ completely. I cannot do that measurement. But nobody stops me from doing the measurement of LX again. Because this system is still in the state of that LX. So one time I should be able, I'm again saying should be able to, and you will say it is a strong statement, but in my mind, I'm thinking like, okay, in principle, I cannot do a measurement of LY, I understand, but I should be able to do the second measurement on LX itself. Why not?
Yes, definitely.
Yeah, so if I am saying that, oh, there are two components to it, one is real part, another is imaginary part, what's wrong if I do the imaginary one measurement real and one measurement imaginary? Like, I'm just thinking in that sense. I understand if you do the measurement of like LX and then you want to know something about LY, that's not possible.
Okay. I think we will have to think hard about this question, because we are not trying to really measure the eigenvalues of any physical observable. Okay. We are trying to measure the wave function itself. Okay. So,
but don't we agree that wave function measurements are not possible?
No.
Like we agree that these psi cannot be measured.
No. Because that's what Rajesh is. I think what we are trying to understand is not trying to measure the LX twice. That will not help, because what we are trying to say that, what Rajesh, let me see if I understand Rajesh correctly, that complex quantity should be measurable, right? In principle.
Yeah, I say just measure the real and imaginary part. And especially if they're connected, or I take a very specific example, refractive index of a material and the absorption coefficient of a material.
Shajesh, I want to point out something again to you here. So I'm pretty sure that you are thinking in terms of epsilon.
Yes.
The dielectric function. But the measured quantity is, as you are saying, refractive index. Now the relation
between absorption also can be measured.
Yeah,
it
absorption.
Turns out that they believe in this relation so much.
I agree.
That they use one to convert the other, but both can be measured.
Listen, I agree. Yeah, both can be measured. But the way you are relating it with epsilon, they are still not the same quantities. Like N is a real quantity, right?
I don't understand what you're saying.
Like when you say refractive index N, that's a real number, right? And epsilon is related to it in terms of a square root of something, right?
Just a minute.
I don't know what you're opposing.
Just a minute. Hello. हाँ बेटा हाँ बोलो क्या है बस कौन हाँ एक मिनट बेटा मम्मा घर पर है क्या अभी अच्छा अरे बेटा रुको, 1 minute रुको.
I think we have already crossed sufficiently, and we can.
Yeah,
I
think
guess we can call it a day.
Yeah,
today.
Shajesh, actually, yeah, I think
If
I will
your
have
son
to-
needs, attend to that. I think this was just discussion part.
Yeah.
We
yeah,
can
yeah.
just
Can
stop
continue
now.
another time. Yeah.
Mhm.
Yeah.
Yeah.
We can,
Okay.
yeah, actually, in fact, also Kausar has invited students today, so we might be going somewhere. So, and of course, his friend has come, so he wants to ask some permission. So he's talking to me, and of course, I had a call from another colleague of mine. Actually, he has undergone some operation today in Jaipur, and he had something to communicate. So I need to get back. हाँ बेटा 1 minute रुको मैं Sajesh, I think I'll disconnect. Okay, I think, but it was nice. I think I just want to make one comment that we need to understand that what does it mean to measure psi. Okay, because in the language of quantum mechanics, then we need to then find an operator's eigenvalues. So this whole question of what does it mean to measure psi itself, to me, is a non-trivial question.
I think psi cannot be measured. That's the way I understand it. But yeah.
No,
anyway, let's continue another time.
We are trying to transcend that paradigm, right?
Mhm.
So if you do that, then we need to understand. We need to ask as to what exactly is meant by measuring psi first, before we think about how to actually measure it. So, yeah,
Okay,
I think
go ahead. Your son is waiting for you.
Yes. I think I'll stop here. And maybe at some other time, all these things can be spoken of in the context of Stern-Dirac experiment as well. But I thought that let me talk about it in a much more elementary context where the whole machinery of cat and bra is not required, and we can just talk about the wave function and the Schrodinger equation and all that.
No, there are a few things I always learn something new. This is what I have realized, and there were nice things here in today's talk.
Yeah.
So it's a good discussion. Yeah. Let's continue sometime. Yeah.
Yes,
all right.
Sure. So maybe these things can be, the same conclusions can be obtained by going to the, understanding the sequential Stern-Dirac experiment. It will force you to have complex wave functions. Okay. We can do that.
Okay, go ahead.
At some time. Okay.
Yeah.
So,
let's end the meeting now.
Okay. Bye.
Bye. Bye, Bipin. Yeah.
Bye.
Bye, Ashwati.